Hi, uh, just a moment. Yeah, hi everyone. Thank you for joining. My name is Max. This is the slide about me. I work at Manychat for more than 6 years. I'm an infrastructure team lead, and one of my responsibilities here is to optimize the performance of our application. And I want to touch today the topic that is very interesting for me, and I really hope it will be also interesting for all of you. I will try to keep it simple and clear. Let's move on. First of all, let's have a look at the agenda. I'll give you more context about the application we have at Manychat, what challenges we had with PHP-fpm, how did we solve those challenges, what new challenges we faced, and how we solved them. And after that, I will share the results, and we will have some time to answer your questions. Yes, as Anton mentioned, Manychat is a chat marketing platform, and we enable businesses to drive more sales and conversations on messaging applications. And this messaging application sync is the important part of this talk. Here's a brief example of how Manychat works. We allow people to scan QR codes or send messages via WhatsApp or Telegram or Facebook Messenger or even Instagram, DM, TikTok, whatever, to the business. Here, business can configure the, for example, AI step, instruct the AI to find out from the customer what color of the elephant the customer prefers. Once AI determines the preferred color, Manychat sends out either blue or pink elephant. This is the simplified example just to highlight that we are dealing with insane amount of incoming webhooks. And to support communication with our customers, we need to respond on a large amount of those webhooks, and eventually we faced the growth problem. Just throwing money and scaling infrastructure didn't work for us, because with PHP-fpm the concurrency we can deal with depends on the number of PHP-fpm processes running. And it didn't scale well vertically with incoming webhooks. And one of the reasons for that is that FPM works per request. So on every request, FPM has to initialize the op cache or take it from memory, initialize the framework of all this auto-loading thing, and then it can run the business logic. And a big chunk of incoming webhooks, it's a pretty simple business logic, like mark the message as read or delivered or something like this. So you need to initialize all the thing to do very little. We solved this by using Nginx and Lua. Some of you who were on the talk in May are very familiar with this, but I will focus on a different topic, so please stay with me. That's just the first part. So we used Lua to offload some simple logic to Nginx. And put all the incoming webhooks into different Redis queues to later process it, and then process those queues with command line PHP workers. And those workers work a little bit different. They initialize the op cache, the framework, autoload once when the worker is started. and then start serving those webhooks with business logic without the need to reinitialize the framework every time. It worked very well for us. Additionally, it solved another problem with the request spikes, so that when there is a big number of requests, we can store them in the queue and process them with a bit delay when we have the capacity, instead of having all the workers to serve all the webhooks at once. So we solved the problem with serving those webhooks, but we faced another problem. Contrary to what PHP command line does, FPM has the possibility to share the memory. First of all, opcache, to share opcache among all of the workers. But less known thing is the internal strings. So under the hood, PHP, instead of storing every string, every duplicate string, it stores the string only once, and just references the memory to this string part, saving lots of memory. Especially when we use authoritative autoload class map. For example, this is the output from our class map. As you can see, we use Amazon library, and there are gazillion of files in it. Also in Google libraries, etc. And we integrate with a big number of third-party systems, and we need to use their SDKs and their libraries, and we need to use this class map authoritative to be able to spawn those workers very fast and autoload fast. In our case, those internal strings take up 4 megabytes of memory of those just autoload strings. Back to the challenge with FPM. Because of this opcache and internal strings sharing, we had more or less acceptable memory usage. But when we started using command line workers, we had to have the opcache and internal strings for every worker the same amount. You can imagine, and it just don't share anything, and we started hitting the memory limits on our servers. And it became even worse with LLMs and other API calls. When we need to call the ChatGPT API and wait for ChatGPT to produce the answer, our worker processes do nothing but wait for the network response, occupying the memory. Yeah, and it became even it started to consume even more memory. Back to opcache. Opcache was designed to support this FPM approach with serving each new request, so that PHP do not need to compile the opcodes for every request for PHP files, and just to read it for shared memory. And we use opcache for command line workers, so that we don't need to compile those files. So we still use opcache for command line, but the problem is it's not shared among command line workers. So I've decided to dig deeper and find out if there is any way to force the command line workers to share something. I've got into the details how PHP allows to share memory. It's pretty simple to share memory between PHP and any other application, including PHP. One just needs to open the sorry. It works. Needs to get the IPC key from some common file, and then using this IPC key attached to the shared memory segment of this size, and then one process can put the variable into this shared memory segment, and the other process can get the variable from there. And this temporary file, it may be not temporary, any file. This file is a common ground between those processes. It's not the file itself, so it doesn't contain the data from this memory. It's just the file descriptor for Linux that allows those processes to attach to the same memory segment. Keeping this in mind, I went to PHP source code to find out how FPM does it with their workers, and I have found that there is a function that also opens the file, but what surprised me that the file was created at the moment of memory initialization, and the file name was unique, and it was deleted right after creation. And when I went searching how the memory is allocated, this file didn't participate in sharing memory. So turns out that I was completely wrong with my assumption. PHP-fpm works completely different. It do not spawn the worker that then attaches to shared memory. Instead, the master processes do all the initialization and just forks the children, and the children inherit the address of the shared memory and the log file that allows to protect the memory segments when multiple processes try to write to this segment simultaneously. And turns out PHP command line has the built-in function pcntl fork that actually does the same. It forks the PHP process into two. So I've decided to make a quick test. In one worker, forked worker, I made the compilation of PHP file, and then in other worker I have checked if the file was compiled, and turns out it works. So the children can share the opcache between themselves. I've made more tests on the real code on our dev environment, and it worked well. So enthusiastic, I went to convince my colleague to try it into production, and yeah, we got seg faults. Seg faults actually not everywhere. We are careful with our rollouts, but some small portion of our users were affected with this. And unfortunately, the issue occurred sporadically under high concurrency circumstances, and it was hard to find it on dev environment without proper concurrency and load. We dug through our segmentation fault dumps, and the only reasonable idea that we had is that opcache got corrupted on the file level somehow, and some processes either tried to write the opcache and other reads, and they are not locking the files properly or something. There is the configuration files to lock the files to avoid that, but in our case, for some reason, it didn't work well, so we got the corrupted opcache judging by the segmentation fault. So we decided to just warm up all the files once on deploy and never recompile those underlying command line files again. The code for this was pretty simple. We just go through all the directory of our bundle file, find all the PHP files, and just compile them. If you will be doing something like this, like we did, don't forget to run this warmer with enough amount with limit of max accelerated files and the limits for memory consumption, and especially for internal strings buffer, because if you try to compile at once like 50,000 files, you will run out of memory in those internal string buffers pretty fast. So keep it as high as possible on deployment preparation. Yep, this solved our problem. The segmentation faults were gone, but Redis got insane. It started returning wrong key values or complete garbage in its responses, and the amount of the connections we made to Redis were growing pretty fast. Yeah, it went crazy. Turns out that when we fork the child process inherits all the file, all the descriptors. In Linux, everything is file, including connection. So the child processes inherited parent connection descriptor and started using the same connection in parallel, and that returned so the answer for one child was returned for the other, etc. And even if we destructed the Redis objects before forking, there was the other problem. We use Redis with persistent connection pool, and when the Redis object is destructed, the connection is returned back to the connection pool to be reused later. But in case of fork, something went wrong, and those connections stayed in the pool and were not reused by the Redis. So they are open but never used, and workers open new connections. So two problems, one solution. Two problems, one solution. We just forcefully close all the connections we have before forking, and the children open their own connections and use their own connections. And this is valid not only for PCNTL fork. Even if you make shell exec and exec some bash script or launch Python or something like this, your file descriptors will be inherited by the shell, by the binary that you invoke. And even if your child process, if you fork, for example, with no hub, so make it keep alive, and you exit from PHP, the second process will still keep these connections. So that was not very obvious for me, but if you actively using exec or shell exec or something to spawn any other workers, make sure you don't have any open files or network connections or database or Redis connections, etc., or you will be using them until your second process exits. Okay, Redis start to behave, and everything else worked well. And here are the results. So this is the FPM consumption, the command line without this fork mechanism, and command line with forking performed even better than FPM. The first reason for this is that if we used FPM as a general purpose serve everything thing, so all the endpoints we have in our application touches every point of our code. So everything is was taken into opcache, and the opcache size itself was pretty large. And with command line workers, we made them dedicated. and so they work with only some part of our code, so they don't need as much op cache for their work. So like we split the monolith without splitting the monolith into microservices, but just by using the dedicated queues. But there is one less obvious thing that saved us more than FPM. It's a cow, copy and write in Linux. When Linux forks the process, it do not copies the memory of this process. It allocates the virtual memory addresses, but those virtual memory addresses are mapped by Linux kernel to the same physical address, unless you make the write to this address. So if you make any change, the part that is not changed keeps intact, and only changed parts are copied and have the separate copy. So you save lots of memory on this. And we make the PCNTL fork after the framework is initialized. So everything that happened in PHP before the fork stays copy on write it unless overwritten. So all the memory that framework uses but don't rewrites is shared amongst all the workers. And it's more or less easier to find out how much memory we saved. Modern Linux kernels have the special proc file smaps rollup. It had the smaps, but it's insane to analyze it. But this rollup thing can roll up and sum and give the detailed information about your process memory utilization. And here I've taken the random worker one of 54 workers. This is a pretty big output. I've damaged my brain several times trying to figure out what is going on, so I've decided to take only a little part of it. So the resident memory, 47 megabytes, it's the memory size of the process if only this was the only one process running in Linux. PSS is the proportional memory part, so the actual memory used by the worker, because it shares lots of parts of memory, including op cache and copy and write. Anonymous memory is the working memory of the process, so the memory allocated itself, and also the part of the memory that is dirty, meaning that it has the copy on write pages overwritten. And the PSS anon is this working memory, but discounted for this shared memory part. So so actually, instead of using 7 megabytes, it uses only 1 megabyte. Thanks to this copy on write thing. Yeah, well, pretty impressive. Yeah, that's it from me. Thank you. I think we can go to questions.